I have assigned to do in class from section 4.6, that is on page 251. We're going to do number 11. You might want to pull to that problem because I'm about to walk through it. Okay, so in that problem we have a sphere like this, and it's being air or helium is being pumped into the sphere. So that helium is being pumped in at a rate of 100 pi feet cubed per minute. So we're going to label that air going in is going to actually affect the volume. It's going to increase the volume. So dV dt equals 100 pi feet cubed per minute. And in the problem, they want to know what is the rate of change in the radius, so dr dt, when the radius is 5 feet. So we need a relationship, and the relationship has to tie the volume to the radius. You should know this, perhaps you don't, but the volume of a sphere is 4/3 pi r cubed, like that. Now the 4/3 pi acts as a coefficient, and we're going to take the derivative, so dV dt equals, if I bring the 3 down, it cancels out with the 3 in the denominator, and I'm left with just 4 pi r squared, because I reduce the exponent by 1, and then times the derivative of stuff times dr dt. And we're again trying to find dr dt, so this is going to be 100 pi at a snapshot in time. This is 4 pi, the radius is 5, and that's squared, times dr dt, and then we just have to solve for dr dt. dr dt equals 100 pi, the pi's cancel, 5 squared, 25, so 1, and that's going to be 1 foot per minute. That's part A of the problem. Now we're going to take a look at part B when it says how fast is the surface area increasing at that very instant. So in part B, we want to find ds dt at the very instant before. So that's when r equals 5 and correspondingly dr dt equals 1. The surface area of a sphere, S equals 4 pi r squared. Not a coincidence that that is the derivative of volume, but anyway, we take the derivative of this and we get ds dt equals 8 pi r dr dt. And at the snapshot in time, ds dt will equal 8 pi, radius is 5, dr dt is 1, so that will come out to be 40 pi feet squared per minute. Next, we will look at section 4.6, page 251, number 14. It's about a flying kite. Again, please turn to that problem, give it a try, and then watch the video to go over the problem. In this problem here, let's see, we have a kite that's 300 feet above. Whoa, that is that's a terrible. There we go. And the kite is flying in this direction like that, and we're letting out the string here for that. So this distance here is fixed at 300. I'm going to label this X. I can label this anything. Maybe I'll label it Z. Okay, so in this problem, what's given is that the kite is flying, I'm reading it here, is flying away horizontally, so dx dt equals 25 feet per second. And we're asked to find how quickly you have to let out the rope, so we have to find dz dt when the rope is equal to 500 feet. Relationship. Looks like good old Pythagorean theorem. 300 squared plus x squared equals z squared. I'll take the derivative. That goes to 0. So 2x dx dt equals 2z dz dt. And then a snapshot in time. 300. This is 500. Another 3, 4, 5 triangle. So this is 2 times 400. Dx dt is 25. 2 times z, which is 500 dz dt. And dz dt equals, let's see if I can't do this in my head, 4 over 5 times 25. Looks like the answer is 5 times 4. Sorry, so the answer is 20 feet per second. That's from the textbook.